Okay, so I think we're gonna start. Good morning, everyone, and thank you for attending to this talk, and thank you, Dario, for joining us today. So a quick introduction, Dario is one principal investigator in the combustion research facility in Sandia National Labs, so one of the national labs in the US. He leads different teams and different efforts related with the aim or reducing the emissions and also improving the efficiency of off-road engines and more other things that people talked about today. So we've been working in a close collaboration for a few months now between UW, the University of Leon in Spain, and also Sandia National Labs. And that's mainly what he's gonna talk about today. So I'm just gonna leave it like that, and the floor is yours. Thank you.
Okay. Thank you. Hello all. So thanks Anna for the introduction. Thanks Steve and Anna for the invitation. It's really nice to be here. My first time in Seattle. So it's good coming from the Bay Area. It's good to feel, cold weather once in a while. I have to unpack my coat from the math room. So that was good. You have a really beautiful campus here, by the way. I don't want to compare it with Sandia, but you'll see some pictures. It's a completely different story. So anyways, today I'm going to present some of the results that Anna actually obtained in a collaboration with us. I know a little bit about combustion. I know nothing about machine learning. So this is going to be kind of a learning experience for all of us. Hopefully you learn something about fuels and fuel design and fuel performance. And I learned a lot about machine learning and how to apply it to solve combustion problems. So let's see. Okay. We start with an unresponsive computer. That's good. Now? Okay, thank you. So first I'm gonna talk a bit about Sandia National Labs. I think I'm gonna meet with some of you later today, probably to talk about how is Sandia, what opportunities are there, especially for PhD students or postdocs. Work a little bit about what we do. And then I'm gonna provide just two examples of recent work in one of my groups at Sandia, where we applied machine learning techniques to solve some problems that I'm sure we couldn't solve anywhere. Finally, there's a final section. It's more an open discussion. So I'm going to talk about the type of data that we collected over 40 years of experiments at Sandia. It's a really well unified, consistent database. I think that has a lot of potential for machine learning problems. And I want to use the opportunity to basically have an open discussion with you and see what you think about it. I think we can apply those techniques to obtain useful information in science. If we start about Sandia, so Sandia is basically one of the three national labs that belong to the National Nuclear Security Administration, together with Los Alamos and Lawrence Livermore. That means that the main research area of Sandia is nuclear deterrence, basically nukes. We have also research in other areas like national security, global security, energy, and homeland security, where I want to, and advanced science. But you'll see on the next slide that probably half of the budget is for the first topic. We have two main campuses, one in Albuquerque in New Mexico. It's the primary site with pretty much, I would say that 80% of the population there, and another campus in Livermore in the Bay Area, an hour away from San Francisco. That is where I live. We have testing facilities as well. But what you can see there is a picture of the combustion research facility. Is actually the building where my labs are in Livermore, California. If we talk about numbers a little bit, so Sandia's budget is about $5 billion annually. You can see there a distribution of the budget for the different, from the different budget agencies and for the different topics of research areas. So 60% is nuclear defense. So it's really the main reason why Sandia works is because of that. If you check the workforce, it's about 17,000 employees. Really, really wide backgrounds. You see electrical, mechanical engineers, but also computing, cybersecurity, physics, etc. And most of them are master's degrees with a big chunk that is basically PhDs that are basically the main research staff, PIs like me, for example. So if we dig into my department a little bit more, again, I belong to the combustion research facility. It was established in the 70s with the energy crisis in the US. And since then, we've been really focused on improving efficiency and reducing emissions for applied combustion applications or energy-related topics. There are different research areas, some of them related to develop new experimental capabilities. For example, the combustion research facility is the first place in the world where we realized that we can use laser diagnostics applied to internal combustion engines to visualize what's happening inside the combustion engine. And you see some pictures of how we do that. We do that with optical engines that are basically modified versions of the engine that you have in your car, in which all the walls are made of sapphire or fused silica, something that we can see through, and apply different diagnostics to basically assess the combustion and mixing and combustion of the fuel in the air. But we have also worked on computation, chemical physics, hydrogen, fusion, and even material science. So for applied combustion, I'll show some examples of experimental results later. I think that we can get pretty cool results, and we have pretty impressive capabilities. For example, these optical engines that I mentioned that are transport engines in which you can see what is inside. We are the only national lab that have in the US. Okay, really brief introduction. I don't want to spend a lot of time talking about Sandia. I want to spend some time talking about fuels. So among all the different research topics that we have in the applied combustion research department at Sandia, research on fuels, new fuels, fuel formulations, fuel properties is one of the key topics. And is one of the topics where we found that machine learning is probably extremely useful. So I'm going to show two different examples, one about prediction of fuel properties, another one about optimization of fuels. And if we talk first about prediction of fuel properties, and this is kind of an open question, but it's more or less a tricky question, so you realize what the heck is a fuel. So can somebody tell me what's the density of gasoline? Guess a number.
6 pounds per gallon.
So the thing about gasoline is there's no good answer. That's the thing, because gasoline is not a thing. Gasoline is not a well-defined substance. Basically, hydrocarbons or real-world hydrocarbons, they're composed of hundreds and hundreds of species. So one batch is going to have completely different properties from a different batch. The gasoline that you buy at South Seattle is going to be different from the gasoline that you buy at another station in North Seattle. And it's going to be different from the same North station in Seattle a different day. So there's a lot of batch-to-batch variability. There's a way to control that, and these regulations. We'll talk about that in a second. But basically, real fuels or practical fuels, hydrocarbons, they're composed of hundreds of species. The way we classify those is with hydrocarbon families. You can see the examples here. You don't need to learn those names or anything like that. But basically, it's a mixture of different chemical components with very different structures. Different structures means different behavior, different combustion behavior. Just to give you an example, this is the composition of a real gasoline. This is a detailed hydrocarbon analysis. It's a list of all the components that you can find in a gasoline. For this specific example, we found 269 hydrocarbons and 28 stuff. We don't know where it is. So typically, you can identify about 96, 95% of the composition of the fuel. The other 5% is who knows. If you plot this wide composition in kind of a bar graph, you see all the variability between the families that I mentioned on the previous slide. So, and the carbon number, that is basically the size of the different molecules. So it's a wide range of things mixed together. And what is interesting is that if I go to the same place and buy a different batch of gasoline a different day, this is going to change completely. So that makes predicting properties kind of challenging because the composition is changing all the time. Among all the properties that we care about, many of those are strongly regulated, like density, for example, the question that I asked a minute ago. So we know that a legal gasoline has to have a density between one value and another value. We know that there are other properties, like, for example, octane number, which is this number that you see at the gas station, that also has to be between one value and another value. I'm going to talk about this specific property that is shown on the slide in a second, because I think that is important. But before we move into that, so we can learn a little bit more about fuels. How many of you buy premium gasoline? Okay, you're all very smart though, because your engine is not, well, it's gonna notice, but it's not worth the price. And now I know that all my collaborators in industry are gonna cancel all the contracts with me, and that's okay. But basically, it's something that I believe that is widely believed out there, that if you put premium gasoline, your engine's gonna perform like in Fast and Furious or something like that. It's not gonna happen, okay? So a property closely related to octane rating, that is that number that you see at the gas station, is the seating number. The seating number measures the quality of a diesel fuel. It's an important, very important property for us because it's regulated for diesel fuel. It has to be higher than 40. So again, it measures quality. So the higher the number, the better the fuel is. It has to be higher than 40 in the US. The diesel fuel that you can buy typically is about 45 or so, but it's not regulated for aviation. So basically, you can have aviation fuel, kerosene, with very, very poor ignition quality, very, very poor seating number. That's not really a problem for civil jets, but it's a big problem for military applications. Here in the US, we have the one fuel policy. Basically, we use aviation fuel for everything, even for diesel engines in military applications. And the problem is that if you put a very poor ignition quality fuel in a diesel engine, it's not going to work. And you know, here in the US, this number, this quality index is always 40 or higher than 40, which is okay. But if you get diesel from, I don't know where, it can be like 15, and it's not going to work. So just to give you an idea about how much this property can change depending on the fuel, we have here plot the seating number of many different fuels. So you can see the typical range. So for a diesel fuel to work well, it has to be within this range here, this interval here. We know fuels that are like twice as good in terms of ignition quality. We have a lot of fuels that are really horrible. Those could be relatively good gasoline fuels, most of them, but really, really bad diesel fuels. So we have this really wide range. It's a property that is not regulated for aviation, but we know that it's important for aviation applications. So that gave us a motivation to basically predict it. And the way we want to predict it is using machine learning. So you can see the approach that we follow here. Basically, of course, this is a data-driven machine learning model. We're going to need good data. So the first part is always trying to collect data that is as reliable as possible. You know way better than I do that if the data is not good, the result is not going to be good. Then trying to train and validate a machine learning model, and finally trying to obtain an explicit formulation. Why is that? Because mechanical engineers like me, we don't like software. We like things that we can do in a piece of paper. So explicit formulations, good. Okay, so to do that, I'm going to talk a little bit about this fuel property. and how we measure that fuel property. So we measure that fuel property in a device that is called an ignition quality test. Fuel properties, all fuel properties follow standards, ASTM standards. The ASTM standard for seating number, for the derived seating number, is this one here. And it basically consists of an experimental test in a closed vessel in which we inject fuel, we let the fuel ignite. Whenever it ignites, we measure the ignition delay, that is the time between the start of injection and the start of ignition. And that correlates with the ignition quality of the fuel, or basically the ignition propensity of the fuel. So we found a database of seating numbers for a number of different species, pure components, binary blends, and also multi-component fuels with 7, 5, 6, 7, 8 species, but that are well defined, that we know what it is, not like the gasoline that I showed before. Then we learn how to replicate this experiment, this test that is the standard for seating number, using modeling approaches. So basically, we know that is a fuel spray injected in a vessel, in a closed vessel, and we're going to measure the ignition delay. So we can simulate the same thing with software that we have. I'm not going to go through the details. Probably it's more related to combustion and to machine learning. But basically, we can predict the same ignition delay that is measured experimentally using our models. So once we have that, and we have that with, enough accuracy, that's going to be a fantastic input for a machine learning model. You can generate virtual data if you have a model that you can rely on. So we did that, and just to give you a really raw example, here we have the ignition delay that we obtained with the model versus seating number for many different fuels. So, there's a trend there. Trends are promising, trends are good. That means that, probably with a little bit of correction, we can have something that is useful. Of course, we did some analysis on basically a correlation between different properties of the fuel, just to be sure that we are not duplicating information. The typical inputs that we have are inputs related to the formulation of the fuel, the physical properties, and of course, this ignition delay, this measurement of the ignition propensity that we obtain from the model. Why are physical properties important? Well, you can imagine that if you inject fuel, the way this fuel atomizes, the way it vaporizes, is going to be different depending on things like vapor pressure, volatility, heat of vaporization. So we know that physical properties are important. And actually, we really want to see those physical properties in the explicit expression. And we did. And I'll talk about that in a second. Okay, we trained the engine model. Basically, we follow two different approaches. One is the black box, the neural network that I know nothing about it. So please don't ask questions. The other one is no, I'm kidding. I have Anna here. So the other thing is the symbolic regression. That is this wide approach that it was extremely useful as an exercise to demonstrate how those machine learning models, they give you things that actually can have physical sense. And I'll talk about it in a second. So we use different training databases, different validation databases. Don't worry about the details right now. Just to show you kind of the key points is we have a database that we call database A that has only single component blends. So no fuel blends. So what happens if you don't use mixtures in the training? Can the model predict the performance of mixtures? Most likely not. And I'll show that in a second. The other database, database B, includes both single component fuels and binary blends. So once you include those blends in the training, can you now predict very complex fuels? That's what we're going to see. So basically for pure fuels, that you can see basically the performance of the machine learning model. We have the neural network here and the symbolic regression here as R for the different databases. Again, B means we have single component fuels and blends. A means we have only single component fuels. And if we trying to predict the performance of pure fuels, everything works pretty okay. Mean absolute error between 3.5 and 4.5. The error is pretty much centered around 0, so no bias, which is good. But predicting pure fuels is not that exciting because nobody uses a pure fuel for a real application. It's going to be crazy expensive. So now if we move to binary mixtures, very simple mixtures of just two fuels, we see that those cases that were trained with data set A, that means that we're trained with only single component fuel information, they cannot predict binary mixtures. They cannot predict blends, which is not that surprising. They know how to handle single component fuels. They don't know how to handle fuel-to-fuel interactions. That means that basically, if you want to predict complex fuels, you need complex data or data from complex mixtures. And this is even more obvious here in these, what we call surrogates, that are very, very complex mixtures, similar to what a real fuel looks like. That when you train those, when you try to predict those surrogates with a model trained with the database that has single component fuels and blends, it's more or less okay. When you're trying to do it with a database that has only single component fuels, it's a disaster. It's basically a disaster because the model, it doesn't know how to handle interactions between components, how to handle interactions between. Just to give you kind of an overview of the performance, we're talking about mean absolute errors of about 3.5, and the reproducibility of the test is about 2 units. So we're close to the reproducibility of the test, which is pretty good. Okay, if we check the explicit expression, and I know this is a very complex expression, I don't want to spend a lot of time explaining everything, just the key points here. This was extremely useful for me as a mechanical engineer to really understand the potential of these techniques, these machine learning techniques, to provide something that actually has physical sense. So what you have here in this explicit expression is 2 terms. The second term is the dominant one. It contributes to the final result way more than the first term. The first term is just a corrector. If we check the second term, there's a component here that says ignition delay. You probably remember ignition delay is the time that we simulate with the simulation that tries to replicate the test, the HTM standard test, is the time between the start of injection and the start of ignition. So it makes sense that this component dominates because actually the Seeking number is a metric for reactivity. The ignition delay is the time that the fuel needs to ignite. So it's a metric for reactivity. So there's a very, very close correlation there, with some minor corrections depending on, this is final boiling point, that is basically volatility. It makes sense. Fuels that are heavier, that they need more time to evaporate, they need more time to mix with the air, it takes longer to ignite. So it's going to affect our measurement or our prediction, sorry. And here the first term is a term that is pretty much 0 for most of the fuels, but it has really high values for some specific families and some specific fuels. And what we found is that the model used term 1 as a corrector for exotic fuels. Things like fuels with oxygen that are not present in gasoline normally, or that are not present in diesel normally, fuels with very unusual properties. And again, this first term also depends on something that we call double bond equivalent, that is kind of a metric for the chemical structure of the fuel, how the fuel looks like. And then the heat of vaporization, that is something that changes a lot when you have oxygen in the fuel. So what we found is basically that the model was able to provide an expression that not only gives good performance, but also makes a lot of sense when you analyze the different terms from a physical perspective. There are caveats, though. There are problems there. The most obvious problem is that to solve this equation, you need the ignition delay. To have the ignition delay, you need to run my model. If I don't give you my model, you cannot do it. I'm gentle, I'll give you my model, but basically you need to be able to run a chemical kinetic simulation. You need to be able to obtain simulation data as an input, which you cannot Google. Basically, you need to do a little bit more. We tried to find an expression that does not include ignition delay, and it was a disaster. Okay, so that's not an option for now. For now, the other problem of this expression is kind of obvious, but kind of interesting. So basically, what happens if in term one, the double bot equivalent is 0 and beta is 0? Now you have a singularity, something divided by 0, and the equation is going to crash. That's something that we didn't take into account at that time, but I believe that is important because we found out that for some combination of properties, this expression is going to give you a something divided by 0 expression. That makes no sense. So something to take into account when you work with software like PySR or any software that is going to give you an explicit expression. Basically do the sanity check that is this expression giving me real numbers or not for the whole domain or not. Okay, so if we move to the second part of the presentation, the second part is more about optimization of fuels for aviation applications. So if we talk about jet fuel, we talk a little bit about gasoline, we talk a little bit about diesel. If we talk about jet fuel is one of the fuels with the most strict standards, which makes sense. You know, if a plane crashes, I don't want to talk about it, but you know what happens. So regulations are very, very, very strict. There's a long list of properties that are constrained for jet fuel. Not reactivity, though, not the seating number, as I mentioned on the previous slides, but things like density, thermal stability, but even things like, you know, electrical conductivity, which seems kind of weird. We need to meet those things. When we talk about jet fuel, we are more interested in something that is called synthetic aviation turbine fuel, or SATF. Some people call it sustainable aviation fuel. We don't do that anymore. So synthetic aviation turbine fuel are basically bio-derived fuels for aviation applications. The main challenge with those is how can we produce enough? And the reason for that is because there's only 11 production pathways approved, because, you know, this fuel has to meet all this list of requirements. So to meet all of that, you need to prove that the product that you obtain is actually a drop-in product. It's something that you can put in a real engine and it's gonna fly and nothing's gonna happen. And that takes a long time, and it's a very, very expensive process because you need to produce thousands of gallons of this prototype fuel just for testing. And at the end of the game, if you realize that the fuel is not good, you basically waste thousands of gallons of fuel produced in a prototype facility. So the whole certification process is very slow, very expensive. There are, among the 11 production pathways, well, you have them listed here. Just, you know, I'll share the slides with you later if you want to know more about this. But basically, that gives us the motivation of, okay, we know that developing new synthetic fuels for aviation is extremely expensive because the certification process is long, it requires a lot of fuel. Can we have a way to, from the very beginning, at least do some pre-screening to know, hey, is this prototype fuel promising, yes or no? If the answer is no, okay, we are not going to spend $100 million in developing the certification process. So we try to do that, combining, again, modeling, more sophisticated or physics modeling with machine learning approaches. So in that case, what we did is we basically have a tool at Sandia that allows us to predict in simulations the performance and emissions of a jet engine. It's called a reactor network. It's basically a series of reactors that numerically they interact with each other and they simulate different parts of a jet engine, of the combustor of a jet engine, where we inject the fuel, where's the flame located, when we put air to cool down those gases, the turbine, the nozzle, etc., even the plume of the aircraft, when we have all those pollutants. So basically, we know that the model works fairly well. We have a validation here for the landing and takeoff cycle. That's the homologation cycle for jet engines. Basically, it's kind of the exam that the jet engine has to pass to put it into the market. And we know that if you pick the real engine and you do the exam, and you pick our model and you do the exam, we obtain the same result, which, gives us some confidence. So what we did, and yeah, you can see some extra validation here. Don't worry about this right now. So basically what we did is, okay, we have this model of a jet engine that we can use to generate tons of data. We know that it works for jet A, or petroleum kerosene. We know that it works fairly well for some synthetic fuels, but there's limited data because there's synthetic fuel availability is not that much. Can we use it to basically generate a numerical database that we believe that is robust enough to train a machine learning model that we can use to tell us, hey, if I have a prototype fuel, is worth spending $100 million in the certification process, yes or no? And this is kind of the approach that we follow. Basically, starting from the database, we generate candidate blends, and we check if they meet the standards. All this list, the long list of properties that I showed a few minutes ago. If we meet the standards, we're good. And then we can test how it performs in the engine model, or in this case, instead of the engine modeling, as machine learning surrogate of the engine model. And depending on the results that we obtain, we decide if this is a blend that we like or not. And we can generate via genetic algorithm multiple blends that optimize a fitness function that we can decide. It can be focused on cost, it can be focused on pollutant emissions, it can be focused on efficiency. So we did that. We generated the database by blending thousands and thousands of fuels and numerically running those fuels in our jet engine model to predict how they perform in the engine, an engine model that has been validated against experimental data. So we try to develop a database that is not biased, that you have a little bit of everything. Pretty much any chemical component that burns is included there. Then with this database, we trained the machine learning model to predict the same results that we obtain with our more sophisticated jet engine model. And we are typically within plus minus 5%, which is probably good enough for this exercise. So basically now what we have is a surrogate of the jet engine model that can be run in a matter of milliseconds, a model that is fast enough for optimization. So basically a model that is fast enough to test millions of candidates to find which one is the best one. And finally, we need to decide, okay, what is a good fuel? And that depends. For fuel producers, it's probably cost or production performance or amount of yield that you can produce. For end users, it's also cost. For regulators, it's probably pollutant emissions. So we tried 3 different fitness functions just to play a little bit with the model and trying to see if we can learn something besides obtaining a good fuel. If we can obtain information that can inform us of why a good fuel is a good fuel. There are 3 examples here. I'm going to show just the last one because of time and because I believe that is probably the most interesting one. So if we go to, yes, this method function 3 is a method function that is really focused on pollutants for the landing and takeoff cycle. The landing and takeoff cycle is the exam that every aviation engine needs to pass to be into the market. So basically, if you are General Electric and you fabricate a new engine, you need to pass that exam to be able to sell it. And this exam measures particle mass, which is basically soot, solid mass of soot, particle number, the number of small particles that are going out of the nozzle, and NOx, that is nitrogen oxides. So what we ask this optimizer, this machine learning surrogate, is give me a fuel with the lowest soot, the lowest particle number, and the lowest NOx. And what we have here is basically in gray the distribution of this merit function, that is the merit function that minimizes particle number, particle mass, and NOx, the distribution in the database, the original database that we generated with thousands of plants that we tested in our simulation tool. And then in, I'm going to say green, the results from the genetic algorithm that is testing thousands and thousands of plants and giving us the optimum. So just for reference, everything is normalized with Jet A, which is standard kerosene. So basically a value of 0 is a fuel that performs exactly the same as Jet A, and the more negative, the better. So we can generate a lot of blends that are better than Jet A and that are legal, that they meet all the standards, but they perform better in this exam that all engines have to pass. But what is really interesting is when we now check among all those blends that are better than Jet A, what's the composition of those blends? What we have here is basically the probability density function of the different chemical families. This is these chemical structures that I show at the beginning of my talk. The different species that are in the fuel. So we can see that for really good fuels, we want to have the orange, we want to have the red, and we want to have the purple. And that gives us a lot of information as fuel engineers to tune our process. So if we can tune our process that our yield give us more purple, more orange, more red, it's going to be a better fuel. Those are the things that we can learn thanks to this machine learning approach, things that we'll never learn if we don't have this capability, basically. Okay, and just to have enough time for some questions, I want to talk about something that is more an open question, something that is more open to discussion. That is one of the databases that we have available at Sandia, and this one is called the Engine Combustion Network. So the Engine Combustion Network is an international organization or international collaboration led by Sandia and with participation from research centers and universities from all around the world. So there are probably 50 or more than 50 different institutions contributing to this database. It's the world's largest database of engine experiments or engine-related experiments. It's publicly available at ecn.sandia.gov. You can go there, access all the data, and you're going to have data about diesel combustion and in both more canonical fundamental experiments and diesel combustion in engines, but also, more unconventional fuels like methanol, hydrogen, etc. So the data is there, and we know that there are people that are using these database to do things related to artificial intelligence and machine learning. That's something we found in the last probably 4 or 5 years, more than 120 papers that basically use that database to apply machine learning and solve problems. And this is something that we found very interesting, something that we believe that has a lot of potential. We are combustion researchers, so we don't do that, but we generate the data, we own the data, so we'll be more than happy to collaborate with others. And just to give you an example, this video here that hopefully is gonna play. Let's see. Okay. I'm not gonna be able to play it all together, but that's fine. So this video here represents experimental data on the whole process of a diesel combustion. So what we have here first is X-ray data of the injector. What we're seeing here is the inside of the injector, how the needle opens, and when the needle opens, how the liquid fuel is injected into the combustion chamber. This is all experimental. It's based on optical diagnostics. Here, by applying basically a light extinction, we can see the liquid. The black lines there is the liquid fuel being evaporated. We have a lot of liquid here in the nozzle and much less liquid here. And then we see the vapor phase, thanks to light scattering. And we can see where the vapor is and how the vapor is mixing. And finally, applying some chemiluminescent diagnostics, we should be able to see the combustion, which is here. So we can see the whole process from the very beginning, how the needle of your injector opens, the fuel goes inside the chamber, it evaporates. One is in vapor phase, it mixes with the air. When it reaches the right conditions, it ignites, and then how it burns. And in the whole process, okay, we have tons of data like this, but we have a lot of open questions as well. One is, for example, the internal flow. You can see how the needle opens and closes. And something that maybe is not that obvious. Oh, sorry about that. Okay. Okay. I'm seeing it here, but I don't see it. Well, anyways, use your imagination. Something that is maybe not that obvious is that the needle bounces. And we know that the internal geometry, the internal flow affects how the spray develops. We don't know how, we don't know, well, we guess why, but we know that happens. We know that if your nominal diameter of your nozzle is, let's say, 70 microns, but because of our ability to fabricate injectors is 71 microns, the injector is going to perform differently. So we have the data, but we are not able to correct for that. This is an area in which I believe that machine learning can be useful to build correctors, to basically understand how very small differences in boundary conditions, very small differences in the actual geometry of an injector compared to the nominal geometry of an injector is going to affect mixing. Then for atomization or for liquid mixing, that is the second part here, we know that if we want to model and spray, there are a lot of knobs that you have to touch, especially in computational fluid dynamics. The models that we use for atomization and mixing, they require some knobs that, it's modeling. You can get whatever you want if you touch the knobs enough. So what we don't know is how those knobs should be tuned for different fuels. We realize that values, constants that work well for diesel, they don't work well for methanol because the properties of those two fuels are very different. And we don't really have a good method to adjust those. But with enough validation data, I believe that machine learning can guide us and tell us how we can adjust those knobs to have more robust, more reliable CFD models. The same happened with vapor mixing. With vapor mixing, one problem that we have when we simulate an internal combustion engine is that it's a turbulent environment. We cannot simulate turbulence unless we do a DNS simulation, which is crazy expensive. So if we do LES, for example, we need equations to basically couple the turbulence that we resolve with the turbulence that we model. And these subgrid closure models is an area in which, well, there are some models out there, we know that they are not great. With enough DNS data to inform machine learning models, we believe that we can make it better, we can do better. And finally, for combustion, probably I want to highlight soot modeling. So soot modeling is probably among all the pollutants the most difficult to simulate, the most difficult to predict. Just because if you think about soot or solid particles, we typically simulate those as spheres, and I'm 100% sure that they are not spheres. So among many other reasons, but basically soot is very, very challenging. So we have experiments measuring amounts of soot, morphology of that soot, properties of the soot, but we still don't know what's the best way to model those things. And with that, I believe that we still have about 15 minutes for questions. So I'm going to stop here. And if you have questions, please let me know.
Thank you, Dario. Now, it's open for questions, so yeah, Mike.
So one of the questions I had, part of my background is in rocket propulsion. So in that, it's a totally different set of rules for like injector design. It's not needle nose. I'm wondering if you've thought about sort of applying this methodology to like injector design itself instead of just sort of modeling the internal flow, but actually sort of solving the inverse problem of injector design, because that's also like very poorly characterized in literature.
So for reciprocating engine applications, we typically don't model the internal flow of the injector. It's going to be too expensive. What we do is we use a model approaches in which the liquid fuel is just a set of parcels that we randomly put inside the engine with the hope that it's going to look like a real experiment. Coupling an internal flow simulation with a full engine simulation, it's completely unknowable. So with that said, yes, we know that internal flow is important, and that's a smart move. Let's do some reverse engineering so we have what we got. The problem that we got with injectors is with tolerance when manufacturing. So let's imagine that you do this reverse engineering, and the answer is you need an injector nozzle of 71 micrometers. But then you go to Bosch or Tensor or Delphi, one of the manufacturers. Hey, I want 1 million nozzles with 71 micrometers, and they're going to be all different because of fabrication tolerances. And we know that those fabrication tolerances are important enough to cause spray behavior differences. That's one of the challenges.
Thank you.
Thanks for the really interesting talk. So in one of your last slides, you showed the database of, I think, the predicted M value versus Jet A.
Mhm.
Jet A was 0.
Yeah.
Why is Jet A so bad in this distribution? Like these are.
Well, Jet A is a petroleum fuel. It comes from petroleum. So one of the components in Jet A is aromatics. Aromatics are a hydrocarbon family that is very important in aviation. We actually need aromatics or fuel systems. The only way fuel systems work is because we have aromatics in the fuel. The problem with aromatics is that they make a ton of soot, a ton of particles. And here in the LTO cycle, particle number, particle mass are two important parameters. So Jet A, in that sense, is a very bad fuel. We know that if we get rid of the aromatics, we can do much better, but then we need to compensate really well for the properties so the fuel system still works.
I have a similar or related question on this plot. So you use this data-driven surrogate to solve an optimization problem to like generate these candidate fuels, and then you evaluate those candidate fuels on like the full, where you have the model you have more trust in to generate this plot. Oftentimes, in my experience, if you use a data-driven surrogate to solve an optimization problem like that, when you get close to optimize, the discrepancy between the data-driven surrogate and the full order model can be really large, because in some sense, really good fuels aren't represented in your training data. And so have you thought about like having a sort of like iterative approach with the data-driven surrogate where you like you train or you solve the optimization to generate these candidate fuels, use those for training with the full surrogate model and like
Kind of an active learning approach, something like that. That's definitely an option. Honestly, the first thing that I really want to do is blend those fuels and burn them. Just to see experimentally, trying to find if experimentally they actually perform and they are supposed to. But that's a very interesting suggestion. We thought about it. For this specific case, I believe that the database is wide enough that we have our ass covered. But in any case, the database is a numerical database. And as an experimentalist, I really want to blend the fuel, burn the fuel, and see what happens. That's, in my opinion, the next step.
If I might jump in, I want to do what you say. Any other questions? Yeah.
Can you go back to the slide where you show the results for the prediction with the database A and database B?
Oh, yes. This one?
Yeah, so it seems to me the mean performance makes sense, and the mixture has lower mean error when you train on the mixture data set. But the variance, like how wide that box or whisker plot doesn't feel like it makes sense because it's like I wouldn't expect the variance of the surrogate, like to start decreasing. But I was wondering if you guys consider looking at the variance.
For the pure fuels, the binary blends, or the sophisticated blends?
The sophisticated ones, do you expect that to be the worst?
Yes.
But it seems like the variance is actually better. I mean, it's worse for the pure fuel.
Or for the database that only includes pure fuels.
Oh, you're not comparing the variance between the different categories.
We are comparing more than the variance, the mean absolute error. So if I got it right, and if not, please excuse me and let me know. So this is 0. So we want to be centered around here, and we want to be as with a variance that is as small as possible, but always centered about here. What happens when we use a database that only has single component fuels and we try to predict complex mixtures is that this is strongly biased. It's very, the mean absolute error is very negative. It's just because the model doesn't know how to mix components because it was trained only with pure fuels. Another good point is that the variance of the model that was trained with blends is larger, but at least it's not biased. It's centered around 0.
When you burn those new candidate fuels, do you have any plans to feed that information back into your models, like a data information?
That would be extremely useful. Yes. Yeah. The thing is, right now the machine learning model relies on a more, let's say, more sophisticated numerical model. So those experiments, to me, they are going to be extremely useful to refine or validate even further the numerical model that we use to generate the database. But absolutely, yes, I think that's a key step. Yeah.
Actually, now looking at this plot, the very on the right, it's not even Gaussian, right? The red curve has a double hump.
Yep. Yep.
What that means is even if the mean is 0, the most likely value is not 0, it's the highest peak.
Which is a little bit towards the positive values. Yeah, yeah, I suppose. Yeah, I think you're right. I need to check. Well, that's the most likely value. The mean is probably around 0, though. But yeah, you're absolutely right. And the thing is, so for this example, those surrogate, what we call a surrogate fuel, is a multi-component fuel that has, let's say, between 5 and 9 species. And this is very representative of a real fuel. But the database that we use for training, it only has binary mixtures of 2 fuels. So that might suggest that even with only information about 2 fuels, you are missing something. When you have plants that are more sophisticated, there might be interactions that we are not capturing.
Any more questions? I am.
More of a general combustion question, but is it also possible to like tune the parameters in the combustion model depending on specific types of fuel so that you could like, you have this type of fuel and you can optimize for that exact type of fuel?
Mm-hmm. Yes, I believe that you need to be very careful when you tune parameters in a model, because the problem is that you can get whatever you want. So you always need to tune those parameters, adjust your parameters based on experimental data that supports this process, that basically supports why you change those parameters. Yes, and that's something that sometimes is missing, especially for synthetic fuels. There's the information that is available is not that much.
You said at the beginning that like cost to make like a pure fuel is kind of like high, and so when you have like these pure fuels, these binary mixtures, it's not like relatively, what was the difficulty
So a real fuel that could be a gasoline like this one. It's very cheap. It's, I don't know how much it's here, but $4 per gallon, something like that. That's extremely cheap. So a research gasoline, that would be a gasoline that we know that is going to have always the same properties. There's no batch to batch variability. There's no this thing that you go to your gas station today and you go tomorrow and it's a different fuel. A research gasoline can be about $60 to $90 per gallon. But then if you go to the pure component, which is, the pure component is, in my opinion, really useless though, and I go through that. But the pure component, depending on the pure component, it can thousands of dollars per gallon or even more. The pure component, it's something that we use because, you know, there's a lot of information about it. It's like, what's the density of an heptane? And heptane is a pure component. It has a fixed value for density, fixed value for viscosity, fixed value for vapor pressure. But real fuels or fuels with applicability, they are not pure components. They are multi-component plants.
Any more questions? Okay, just one last question that I know the answer, but I think it's good to talk about it. Why do you think that it's useful to use many different chemical families where you're trying to find a new fuel and not stick to the ones that are within the standard?
Oh yeah, that's a good point. That's something that I didn't mention. And one thing about specifications for jet fuel, I mentioned that they are very, very strict. They are so strict that if you try to enforce absolutely all of them, there's pretty much only one answer, that is kerosene. And this is on purpose. So you always have the same fuel for those engines. So something that we did in this study is we match all the physical properties, but we let the composition be whatever you want. If that means that the composition of the synthetic fuels that we generated can be something that is not fully legal in the sense that it has chemical families that are not included in kerosene, like components with oxygen or components that are, let's say, unusual. But, you know, this is research, so I believe that it's important to be more open-minded and see what you can achieve if you give some flexibility. So we are meeting all the physical properties. We are meeting all the properties related to how the fuel burns, but the composition is more exotic than that of kerosene. And I think that is okay, especially for research.
Thank you. So I think if there's no more questions, thank you, Dario.
Thank you. Thanks.